Okay, so let's get started. So let me know if the sound quality is not good, or if there's ambient noise that needs to be reduced. So let me start with a summary of what we did last Tuesday. We introduced the Lagrangian, and the Lagrangian was defined to be T minus V, where T is kinetic energy and V is potential energy. So far we only did this for a single particle. And then we found that D'Alembert's equation, or D'Alembert's principle, could be rewritten in terms of this Lagrangian and give an equation of motion of the form d by dt of di-L by di-Qj dot minus di-L by di-Qj equals 0. And it's equal to 0 if all forces are what we call monogenic. Monogenic just means conservative, but it also includes the magnetic force. So the magnetic force is not simply given by the gradient of a potential, like a conservative field. It's given by a little bit more complicated expression based on the generalized potential. That's really the only difference between a monogenic and a conservative force. This monogenic is an expanded definition of conservative so that electromagnetism can be included mathematically in the same way. Okay? If there are non-conservative forces or non-monogenic forces, then the equation of motion is the same, but instead of equaling 0, it's equal to the jth component of the generalized force. And the generalized force is given by the dot product of an applied force dotted with di-Ri by di-Qj. So this second equation is true if there are non-conservative forces. Remember that most forces are in fact conservative or monogenic. Monogenic. Okay? So far, the way we've done it is the sum of the forces has been over the forces on one particle. And then we did an example of a simple block sliding down a ramp with friction. So we had a non-conservative force of friction, and then we had kinetic energy and potential energy from gravity. And we saw that we did get from these equations the correct expected behavior for the equations of motion, namely what you would get from Newton's second law. Okay, so today we're going to keep exploring this Lagrangian and do more examples of applying it to physical situations. And that's what we'll do again on Thursday. Any questions about this? So that'll be the end of the summary. So far, we have considered one particle described by n degrees of freedom so the set of variables qj and multiple forces applied. To the particle. Now, if you remember D'Alembert's principle, when we did the derivation, at some point we ended up with capital T for the kinetic energy. And we found that that was the sum of the kinetic energies of all the particles. And when we did D'Alembert's principle's derivation, we assumed that each particle had one force exerted on it, and that there were many particles, each with one force, and ultimately you could sum up all the kinetic energies. Then we saw in the Lagrangian derivation from D'Alembert's principle that if you consider one particle with many forces on it, you could add the forces from each potential energy. So I'm only talking about the monogenic side, not the qj when it's not equal to 0. So we found that we could sum all the forces acting on one particle into separate potential energies that added up into one total potential. So mathematically, there's really no difference when we're doing Lagrange's equation in considering the system to be composed of many particles, so that T is now the sum of the kinetic energies, and V could be many forces on many particles, and so that it's the sum of all the forces. So mathematically, there is no distinction in extending this to multiple particles with multiple forces. So what I mean is, we can immediately generalize this. So for multiple particles, we can extend the total Lagrangian of the system where T is now total kinetic energy of the system, total kinetic energy of system, so multiple particles, and maybe objects, extended objects, and then B is the total potential energy of the system. And so then the set of generalized coordinate qj are now the coordinates to describe the entire system. And it's not worth rederiving the Lagrange equation of motion by saying that now the sum from I equals 1 to n is over all the forces on the system instead of all the forces on one particle. It's mathematically exactly the same. So we now arrive at a description where if there are not if all the forces are conservative or monogenic, we can describe a complicated system by finding an appropriate set of generalized coordinates and then writing out the potential energy and kinetic energy of the system in those generalized coordinates. And then the Euler-Lagrange equation gives us the equations of motion for all of those generalized coordinates. So it allows us to describe how the system evolves with time. So let's do a simple example of this. Example 4.3 in the notes. It's the same example as we did before, except now we'll have two blocks sliding down around instead of one block. So this is example 4.3. So we have a ramp. And the ramp makes an angle theta. There are two blocks on it. Let's call the first one M1 and the second one M2. And let's say the blocks are linked by an incompressible massless rigid bar of length L. And furthermore, let's assume there are forces of friction on these blocks equal to lowercase f1 and lowercase f2. So we want to use the Lagrangian to find out the equations of motion for the system. So you know from Newton's second law that you consider this, since the masses are connected by a rigid rod, you could pretend that this is a single object of mass m1 plus m2 with a total force F1 plus F2 going upwards, and then gravity of m1 plus m2g going downwards, and then a normal force, and solve for the equations of motion that way. But instead, we'll use the Lagrangian method. And eventually we'll write down a procedure for doing this. But for now, we'll just keep exploring how these problems sort of work out. So let's introduce a coordinate system. So for a Lagrangian description, you need to define these generalized coordinates, and so you really need to have a coordinate system. So let's put an origin there. Now we have 2 point particles. Our mass is m1 and m2. And so they can be described by a position vector. So let me call the first vector r1, and then the second vector r2. So the next thing we need to do is figure out how many degrees of freedom, right? So we have 4 possible degrees of freedom if it's confined to the xy plane. So in principle, there's 6 possible degrees of freedom if they're allowed to move in and out of the page. Well, let's assume they're fixed to the plane. So there's, in principle, 4 degrees of freedom, x and y. But now, x and y are not independent, right? You have, for example, that y1 over x1, so the y position of block 1 over the x1 position, or the x position of block 1 is equal to tan theta. Similarly, y2 over x2 is equal to tan theta. So there it looks like that reduces the degrees of freedom to 2. And then there's one more constraint, and that constraint is that I could write it as x2 minus x1 squared. Is that right? Plus y2 minus y1 squared is equal to L squared. So basically the blocks are separated by a fixed distance L. So there's only really one degree of freedom. So I only need one scalar to completely describe the system, and I can choose something. And so I'm going to choose the variable which I call R. And what I mean by R, I mean the distance from the origin. So it's not a vector, it's a scalar. It's the distance of the first block. So R is equal to the length of the R1 vector. So I can always specify, if I just give the number R, I can completely specify the system, because you know the M2 is a distance L along the plane higher than M1. Okay? So the kinetic energy is always easy to write out in Cartesian coordinates, right? So to get the Lagrangian, right, we need L equals T minus V, so we need to know T and V. So T is always easy in Cartesian coordinates because it's a half M1 x1 dot squared plus y1 dot squared, z1 dot is 0, and then plus, for the second mass, a half M2 x2 dot squared plus y2 dot squared. So the kinetic energy is always used in Cartesian coordinates because it's each of the Cartesian coordinates dot squared added to each other to get V squared. So what we really need is we need x1 dot, y1 dot, x2 dot, and y2 dot in terms of our generalized coordinate, which is R. So that's relatively easy to read off of the diagram. So we start by noting that x1 is R cos theta. So theta is a constant, right? Theta is the angle of the incline. So if I do d by dt of R cos theta to give me x1 dot, then cos theta is simply a constant, and I get R dot cos theta. So similarly for all the other ones, y1 is R sine theta, and so y1 dot is R dot sine theta. x2 is going to be equal to R plus L cos theta. And so x2 dot is going to be R dot cos theta plus L dot cos theta, right? But L is a constant, so L dot is 0. And so that's also going to be equal to R dot cos theta. And similarly, y2, which is R plus L sine theta. If I take the time derivative of that, y2 dot, I get R dot sine theta. Okay? So the kinetic energy, T, is a half M1 times x1 dot squared, which is R dot squared cos squared theta, plus y1 dot squared, which is R dot squared sine squared theta. And then the kinetic energy of the second particle is a half M2 x2 dot squared, which is r dot squared cos theta squared, plus y2 dot squared, which is r dot squared sine squared theta. So that simplifies, right? In both cases, I can factor out an r dot squared, and then I have a cos squared plus sine squared, which is equal to 1. So I get a half m1 plus m2 r dot squared. Okay? Now we need potential energy. So let's go back to our diagram. So the friction forces are non-conservative or non-monogenic, so clearly we're going to have to handle them the annoying way. But the other forces that are acting on our bodies, in this case, is only gravity, and that we can write out as a potential energy. And then the normal force, of course, as usual, we don't care about the normal force, right, because it can do no virtual work. And it's an internal force to the system. So we have the potential energy of the system. We have to take into account the gravitational potential energy of both of our masses. So the first mass, oops. Sorry, that happens when I put my palm down before my pen. The potential energy of the first mass is m1 g times y1, right? Gravitational potential energy, mgh, and the height of mass m1 is y1. And then the potential energy of the second mass is m2 g y2. Of course, we want this in terms of our generalized coordinates. So we have m1 g y1, so it's m1 g, and then y1, we have it up here, it's r sine theta. And then m2 is m2g, and then y2 is r plus l sine theta. So the Lagrangian, we can now write it out, T minus V. So T is a half M1 plus M2 R dot squared, and V, so minus V, so it's minus M1G R sine theta minus M2G, I'm going to split that R plus L up. So it's minus M2G R sine theta, and then it's minus M2G L sine theta. Okay? Now let me just note this last term here, that's a constant. Right? M2GL sine theta is a constant of the problem. It's all constants in there. And the reason that that's a relevant point to notice is that when we do the Lagrange equation, the Euler-Lagrange equation, we exclusively take derivatives of the Lagrangian. And so we have this constant term. So when we're going to take the derivative of that constant term, it's going to drop. So another way to view this constant term at the end, this constant term actually comes from the potential energy, right? It's the second term of the potential energy. So adding a constant to the potential energy is the same thing as saying, well, I'm just going to change my definition of what zero potential energy is. So we could have probably found an origin for the system where the potential energy from the last term would have just canceled. So if we've taken the origin as between the two masses, I think the last term would cancel. All right, so, and we'll go through this formally, but here's already the first view of if you add a constant term to the Lagrangian, it doesn't really change the physics of the problem. You're basically just redefining what you mean by zero energy. And it's only really changes in potential energy, as you recall, that make a difference. Okay? So we have the Lagrangian. So unfortunately in this problem, before we write down Euler-Lagrange equation, we need to deal with the right-hand side, which is not equal to 0, because we have these two non-conservative forces. Okay? So we only have 1 degree of freedom, so we only have one component of the generalized force. But there's two forces that go into that sum. All right? So let me write out Qj, which is really going to be equal to Qr, because there's only 1 degree of freedom. And so that's the sum from I equals 1 to 2 for the two non-conservative forces. So that 2 is F1 and F2, the two friction forces. And it's defined to be Fi dotted with di Ri by di Qj. But di Qj, remember, is R. Or Qj, sorry, is R. So before we can do this, we need to write out everything in terms of vectors so that we can do this scalar product. So let me write out all the forces. So let's say that F1, the capital F1, we'll say that that's the same as the friction F1 force. So if I look at the friction F1 force, it has a magnitude F1, and then it has an x component that's in the positive direction, so it's cos theta x hat, and then it has a positive component in the y direction, so sine theta y hat. F2, sorry, capital F for just the general form in the sum there. We're going to set that equal to our friction force F2. If we write that out as a vector, F2 is the same thing, right? A magnitude of F2, and the direction is positive in x and y, so it's cos theta x hat plus sine theta y hat. And so those are going to be dotted with di Ri by di R. So we need to know R1 and R2 in vector form. So R1 vector, it has a magnitude of R, and then it's also cos theta plus sine theta, cos theta x hat plus sine theta y hat. And the R2 vector, where the second force is applied, it has a length of R plus L, and the direction is again cos theta x plus sine theta y hat. Okay. Any questions about setting that up? So what we really need in the dot product is di R1 vector by di R. So di by di R of that R1 vector, it just removes the R, right? So that's just cos theta x hat plus sine theta y hat. And similarly, when I do di R2 by di R, so I have the R2 vector, you can see it as a sum of two vectors, right? It's the first vector, which is R times cos theta x hat plus sine theta y hat, plus the vector L cos theta x hat, L sine theta y hat. So when I do di by di R of that, anything with an L in it, just di by di R of L is 0. So that term's not going to matter. The only term that's going to matter is the R cos theta x hat plus R sine theta y hat. And when I take the derivative, I'm left with exactly the same thing, cos theta x hat plus sine theta y hat. Okay? So that means that F1 vector dotted with di r1 by di r, the first term in that sum. So if I look at f1 vector, it has a magnitude of f1. Oops. And then the dot product is between cos theta x hat sine theta y hat and cos theta x hat and sine theta y hat. So it's the dot product of a vector with itself, which is equal to 1, because it's a unit vector, but let me write it out explicitly. So that will be cos squared theta plus sine squared theta, right? The dot product of the x components gives cos squared, the dot product of the y components gives sine squared, and then cos squared theta plus sine squared theta is equal to 1. And then for the second force, F2, dotted with di R2 by di R, well, that's simply going to equal F2. It's the same thing, right? It's F2 times cos squared theta plus sine squared theta. So what that means is Qj, which we've called QR, is the sum of those two things. The sum of those two things is F1 plus F2. Now we can finally write out our equation of motion, right? We want to use the general form, which is d by dt of di L by di Qj dot minus di L by di Qj equals capital Qj. And we're going to do this for Qj equals R. So we want d by dt of di L by di R dot minus di L by di R. And that's got to equal to the QR, which we found out to be F1 plus F2. So just because I don't want to go back and forth too much, let me rewrite the Lagrangian, which we'd already found. That was a half m1 plus m2 r dot squared. And then it was 1 minus, I don't remember it by heart, m1 g r sine theta. Minus, well actually, let me write that. Both the m1 gr sine theta and m2 gr sine theta are the same, so that's like minus m1 plus m2 gr sine theta. And then the last term, which was the constant, was m2 gl sine theta. Remember, I made a comment earlier that this last term I don't think is going to matter. So we have our Lagrangian and we have our equation of motion, that we just have to fill it in to get the equation of motion with the generalized coordinates. So there's three things that we need in the equation of motion. First thing we need is di L by di R dot, right? So di L by di R dot, only the first term has an R dot in it, and if I take the derivative of the first term with respect to R dot, I get m1 plus m2 times r dot, right? So the derivative of half r dot squared is r dot. So now 2, I need d by dt of that. So that's d by dt of m1 plus m2 r dot. Now m1 and m2 are constants, right? The masses don't change with time. So when I take the derivative, I just have m1 plus m2 d by dt of r dot, and we just call that r double dot. And the last term that we need is di L by di Qj, which is di L by di R. Sorry, let me just write that as di L by di R. So if I look at L, only the middle term has an R in it. So if I do di L by di R of that middle term, it's m1 plus m2 g sine theta times R, or minus at the front there. So that derivative is minus m1 plus m2 g sine theta. Right? And so now we have everything, so we should put it all together and see if this gives us an equation of motion. So I have the first term, which is m1 plus m2 r double dot. And then, remember, it's minus diL by dr. So it's going to be plus m1 plus m2 g sine theta. And that's got to equal to what we had on the right-hand side, which was f1 plus f2. And if you prefer, we could just write it as f equals ma. So the ma part is m1 plus m2 r double dot, and that's got to be equal to f1 plus f2 minus m1 plus m2 g sine theta. And that's as expected from f equals ma. So this is Newton's second law, right? And it's done in a coordinate system where one coordinate is parallel to the incline. So the total mass, m1 plus m2, times the acceleration along the incline, which is called r double dot, that's equal to the sum of the forces along the incline. So F1 and F2 are both positive. So they're positive in the direction of r dot, or r being positive, right? And then minus the parallel component of gravity, which is g sine theta, times m1 plus m2. So it works. Right, so now we've done two examples where this works. And I've written it really slowly, and I realized you could have written this out from the beginning with a little bit of thought in Newton's second law. But the idea here was not to do this simple problem in a more complicated way. The idea was to show you a general way that is generally more simple. So we now have a procedure, and in particular, if we don't have any of these non-conservative forces, then it's really easy because you only have to do the t and the v. And most systems in the world, in physics, are conservative. So we don't usually need to do this little blurb here where we do the non-conservative forces in generalized coordinates. Okay? Any questions? I'm sorry, there's a lot of noises. I hope, is it disturbing, or it should end soon? So you might have noticed, and I've pointed it out a few times, that we keep ending up with this Euler-Lagrange equation, and it looks an awful lot like something you get from variational calculus, right? So I'm just going to point out, and we're going to look at this in more detail, I think, in the next lecture. So I'm going to mention Hamilton's principle as a way, as sort of a guiding principle for obtaining the equations of motion for a system. Right, and Hamilton's principle says that the equations of motion for a system are found by minimizing, or I'll say by minimizing what's called the action. The action S is defined to be the integral from time A to time B of some function L dt. Okay, so this S here is called the action. So L, this function L, is a function of Qj dot, and T, and we'll eventually go back and conclude that this is the Lagrangian. All right, but for now I'm going to take this as given. We'll show this later. Because it seems a little bit arbitrary that just saying t minus v, I'm going to take the integral of that, and that gives a stationary value. So the condition for that to be stationary gives the equations of motion. That seems arbitrary, right? And it turns out it works. So if we forget about that arbitrary part and we take it as given that this L is the Lagrangian, then from variational calculus, we know that the condition for that integral to be stationary is that d by dt of dial by diqj dot minus dial by diqj equals 0. And we know from D'Alembert's principle that if we do this with the Lagrangian, we do to get the right equations of motion. And so we know from D'Alembert's principle that if L is the Lagrangian, this gives the correct equations of motion. Right? So somehow it's connected to variational calculus. And this Hamilton's principle, regardless of what this function L is, we know that once you get the Euler-Lagrange equation, that if that function L is what we've been calling the Lagrangian, this t minus v, then you do indeed get the equations of motion. So we verify that this is in generally, it's true if you choose the right L. And then later we'll look at, well, what if you choose a different L that's not t minus v? What could L possibly look like? And then we'll find that L has to look like t minus v, mathematically. Okay? But for now, I'm more interested in the idea that this looks an awful lot like variational calculus. Okay? Now, what did we assume when we came up with the Euler-Lagrange equation? This d by dt dial by diqj dot minus dial by diqj. So we've made some assumptions. So far, we have assumed that the system that we described is holonomic. So holonomic, what we've assumed is that all the QJs are independent. So the example that we just did, right, we had two masses connected by a rod, and we argued by ourselves, we brought the degrees of freedom down to 1, and then it's a holonomic system because that 1 degree of freedom is obviously independent. But maybe we derived a description that had 2 degrees of freedom that were independent, and then we know that because those degrees of freedom are independent, we can apply the Euler-Lagrange equation. But if you remember back in variational calculus, or in the example that we just did, when we eliminated one of the variables, that was a little bit arbitrary. Instead of using r, which was equal to r1, I could have used r that equals to r2. And so maybe I shouldn't have eliminated r2, I should have eliminated r1. So it's a little bit arbitrary, right? And so we remember that there was a method to not remove arbitrarily certain degrees of freedom. And that was the method of Lagrange multipliers. That allows us to have these extraneous degrees of freedom, and then it sort of handles them in a symmetric way so that we don't eliminate 1 degree of freedom arbitrarily in favor of another. So if the Qj are related by holonomic constraints, so let me write out a constraint. Maybe I'll write it as lowercase f1 of q1 and then all the way to qn equals to 0. So that's the constraint equation. That's an equation that relates 1 degree of freedom to another. So from variational calculus, we know that we can build a new function L bar and treat all the Qj's as independent. So we can treat all the Qj's as independent by using Lagrange multipliers. So this function L bar, remember, we can define it to be L minus lambda 1 f1 minus lambda 2 f2, etc. if we have more than one constraint. There's a bit of a typo in the notes. The equation 413 should be L equals L bar minus lambda 1 f1, etc. Not L bar minus all those things equals 0. Let me just note that equation 413 is wrong in the notes. And I will update it, so it's only wrong until I've updated it. So we know that when we build this modified Lagrangian, L bar, then the equations of motion are given by d by dt of di L bar by di Qj dot minus di L bar by di Qj equals 0. Alright, I'm going to stop writing the case when it's not conservative. So it's, from now on, I think it's almost always going to be equal to 0 on the right-hand side. So let's go back at L though, at this L bar definition. So recall L is T minus V. So if L bar is L minus lambda 1 F1, that's equal to T minus V minus lambda 1 F1. So lambda 1 F1 is like an additional potential energy term. So we could say V1 maybe. Let's say that that's lambda 1 F1. So then maybe di V1 by di Qj is a force. I remember a potential, so a potential energy, to do grad of the potential, or di V by di the coordinate, you get the force associated with that potential energy. So this Lagrangian multiplier term at the end, mathematically it looks like a potential. And so maybe if you take the derivative of it, it looks like a force. That's just mystery, curiosity at this point. All right. So more generally, the terms lambda I Fi can be used to define, I'm going to put force in quotation marks. So it could be defined, it could be used to define a force which I'll label as Qij. And Qij would be defined to be lambda I. So the I index is for which lambda there is, in case there's only one lambda. And then it's the term for a generalized force. So I really think that's both options. I'm sorry. They're moving a bunch of equipment next to me, so that should move. That should quiet down quickly. And then it's so lambda is a constant, right? And then it'll be di Fi by di Qj dot minus di Fi by di Qj. So the I index is for which constraint equation I'm using. So remember, the F's are constraint equations, and then J is which degree of freedom. So there appears that, at least mathematically, these Lagrange multiplier terms that you add can be mathematically used to get some sort of force. Now, whether that has anything to do with any real force, that's something that we'll look into. At least mathematically, right, these look like adding more potential energies. All right, so let's do an example of this. This is example 4.4 in the notes. So example 4.4, we again have an inclined plane. And our inclined plane makes an angle theta. And on the inclined plane, we have a hoop. So this is a hoop of mass m and radius capital R. And it's rolling down the incline. So this is a hoop, and it's rolling without slipping down an incline. So just like all of these problems, the first thing we need to do is to come up with a set of degrees of freedom that allow us to describe the system. So let's have some coordinates. So let's put an origin at the bottom there. So this is a rigid body, right? It's not a point mass. It's a rigid body. So in principle, there are 6 degrees of freedom. It's confined to be along the plane. So let's say z is always 0. That's 1 less degree of freedom. The hoop could be rotated in 2 different ways about its the axis that's perpendicular to the plane and the axis that's parallel to the plane. But we're going to say the hoop does not rotate one way or the other, so it stays aligned with the plane, so it can keep rolling down along the plane. So that's another 2 degrees of freedom to be lost. So potentially only 4 degrees of freedom. Now it rolls without slipping, so all the remaining degrees of freedom really will reduce to 1, right? All I need to do is to say how high up the plane the hoop is, and because it rolls without slipping, I know that I can always find all the other coordinates. So in particular, let's say we have phi to describe how much the hoop is rotated. And let me use r, the scalar r, lowercase r, as the position of the hoop on the plane. So either of those 2 would be good enough, right, to describe the system completely. If I specify r at any point along that plane, because it's rolling without slipping, I can determine what phi was. And then conversely, of course, if I know phi, I can find r. So if we make it so that phi is 0 when the hoop is at the bottom, right? So let's say rolling without slipping, or rolling without slipping is actually a constraint on the velocity of the point of contact being 0. So it's really a constraint equation that you would have to write as d lowercase r equals capital R d phi. And that's integrated trivially to be lowercase r equals capital R phi. And then we'll say that phi equals 0 at r equals 0. Otherwise, there'll be a constant term in there. Okay, so there's only 1 degree of freedom. And so we can choose lowercase r or phi. Because anytime I have an r or a phi, I could just replace, I could use that equation to remove one of them. Right? So far, everybody convinced that this is a 1 degree of freedom problem? And that either r or phi or x or y would be all suitable coordinates, right? So what I'm going to do here now, I'm going to say, maybe this is a hoop where I need to know the rotation of the hoop, and I need to know where it is. And I want to know both r and phi, so I don't want to just get rid of r or phi. I want to keep both of them in. Okay? So we choose to keep both r and phi, and then use Lagrange multipliers.
So the thing is, I would say one person is,
So our equation of constraint,
one person is not, and they light a candle, or are you going to, yeah.
which would be f of r and phi, that equation of constraint, remember f has to equal 0, so that's like saying that lowercase r minus capital R phi equals to 0. So this f of r and phi is defined to be lowercase r minus r phi. So I can write the constraint between my two coordinates this way. I could write everything in terms of r or phi, but I'm going to choose to keep both, but I'm going to carry around this constraint everywhere. Okay. So there's no non-conservative forces, right? So I can do the Euler-Lagrange equation, and then I'm going to have equal to 0 on the right-hand side. So I need to know, oops, I need to know L bar, which is going to be L minus lambda, or I don't need a 1, I'm just going to call it lambda, lambda F. We already know F, so we need a L. So L is T minus V, and so we need T. So what is the kinetic energy of this hoop as it's rolling down the incline? Remember, this is a rigid body, or it's a hoop with the moment of inertia, right? And so it's going to have both rotational and translational kinetic energy. So T, the rotational kinetic energy, will be a half capital I phi dot squared. So that's rotational. And then plus a half m VCM squared. So VCM is the speed of the center of mass. So if I plug in the moment of inertia for a hoop, so a hoop has moment of inertia mr squared, capital M, capital R. And then the speed of the center mass of the hoop, well, that's just what we called r dot, right? R is the position of the hoop from the origin. And so the time derivative of that is the speed of the center mass of the hoop.
No, they've been white. All you do is wipe them before they go into the freezer. But with gloves.
Okay. Now, kinetic energy, potential energy V,
That's why you kind of just have to position yourself.
for the hoop,
Through handing
it's going to be mg, and then the y position of the center mass. And so the y position of the center mass, so that's going to be mg r sine theta, right? The y position of the center mass here, this distance here is r sine theta. And the center of mass itself is a little bit higher than that, right? The center of mass is actually, I don't know, let's call that distance b, from where r sine theta is, right? Now when we're at the bottom, or for calculating the potential energy, this term b is like, is a constant, right? It doesn't depend on where you are along the incline. The difference in the height between the point of contact, which is at r sine theta, and the center of mass is going to be a constant. So when I write the potential energy, it's going to be the mg r sine theta plus, you know, mg b, I guess. but this is a constant. If you remember from the last problem, that term just drops, because ultimately we're going to take derivatives of L, and taking derivatives of a constant doesn't matter. And that's because it's mathematically equivalent to redefining what zero potential energy is. And here it's not just equivalent, it is where we define zero potential energy is. So I'm just going to define the zero potential energy to be at a distance d above the origin or something like that. So hopefully I've convinced you that I really don't need this last term, and I'm not going to keep carrying it around. So I'm going to use for the potential energy only the mgr sine theta. So that means I can now write out the Lagrangian, L bar. So it's T, which is a half capital M capital R squared phi dot squared plus a half capital M lowercase r dot squared, and then minus V, which is minus capital M G lowercase r sine theta. And then, since I'm writing down L bar, I need to write down minus lambda, and then my function f, recall, was lowercase r minus capital R phi. And so that's our Lagrangian. So we have 2 degrees of freedom, r and phi, and we've decided to keep them both and add in this last term from the constraint between r and phi so that we can keep both terms. Okay? So let's go ahead now and do the Euler-Lagrange equation for r and phi. Right? So the first one we need to do is d by dt of di L bar by di R dot minus di L bar by di R equals to 0. So first I need di L bar by di R dot. So there's only one term that has an R dot, and so that's the half mr dot squared. And when I do d by dt of that, I'm going to get mr double dot. So I have m lowercase r double dot, and then that's got to be minus di L by di R. So I look at terms that have lowercase r's in it, and the second last term, minus mgr sine theta, has an r in it, and then the second last term, the minus lambda r, also has an r in it. So it's minus di L by di R. So both those terms are negative. So if I do, let me underline the red term. So di L by di R of that, so the minus signs will cancel. So that gives me plus mg sine theta. And then let me do in blue the minus lambda r. If I take the derivative of that, I just get lambda. And that's got to equal 0. Okay? So then we do the same thing for phi. So we need d by dt of di L bar by di phi dot minus di L bar by di phi. That's got to equal 0. Now I go back to my equation and I look at the terms. So the terms in phi dot, there's only one. It's the first term. So when I do di by di phi dot, the squares cancels the 2. And then everything is a constant with respect to time except phi dot. So I get, when I do the d by dt, m capital R squared phi double dot. And then the only other term that has a phi in it is the minus lambda times minus r phi. So in the Lagrangian, that's positive, right? That's plus lambda r phi. When I take the derivative with respect to phi, I get lambda r. And then in the Euler-Lagrange equation, I have to take a minus of that. So I get minus lambda r equals to 0. So we have these two equations of motion, right? Now we're not done. So these are equations of motion, but we're not quite done because we have this random lambda in here that we don't know what it is, right? At this point, we don't have an expression for what lambda may be, right? So we need to get rid of lambda, but we only have two equations, and r double dot and phi double dot are unknowns, right? So we're going to have two equations, three unknowns. So to get rid of lambda, we need the constraint equation. So the constraint equation was that lowercase r equals capital R phi. Now, if I look at the two boxed equations, that's not going to help me much, right? Because in the boxed equations, I actually don't have any lowercase r's or phi's. I only have r double dots and phi double dots. So this constraint equation, as is not really doesn't add, because it involves completely different variables. It's not going to help us get rid of lambdas. It doesn't add any information, at least not in the way that we can handle. However, we can manipulate this equation so that it becomes the third equation in a three-equation, three unknown problem. So the main difference is that this equation doesn't have r double dots or phi double dots. So there's an easy way to make that happen, and that's just to take the derivative of this equation. So I take the time derivative of this equation, I get r dot, lowercase r dot equals capital R phi dot. If I take the time derivative again, I get r double dot equals capital R phi double dot. Now we've effectively, we're almost going against our original intent, because we're going to use this equation, of course, to eliminate one variable in terms of the other. And that was the whole point, to avoid that with the Lagrange multipliers. But we're not doing this to get rid of r double dot or phi double dot. We're doing this to get rid of lambda, so that we can keep r double dot and phi double dot. But you can see how this could let you get rid of everything. All right. So let me label these equation 1, 2, and 3. So let me take equation 2. So equation 2 tells us that capital MR squared phi double dot is equal to lambda r, right? I'm just going to move the lambda r in equation 2 here to the other side. But we also have that lowercase r double dot is equal to r phi double dot. So that means I can rewrite this as m well, so that means that phi double dot, right, is going to be R double dot over capital R. And so if I put that into there, I have M capital R lowercase r double dot equals lambda capital R.
Yeah. And now you can check by the way you turn one of them and have it sitting on the fire. Like the other side.
Now the other equation that we had, equation 1 told us that M lowercase r double dot plus capital M G sine theta plus lambda equals 0. So if I look at equation 2, the r's cancel here, right? So M lowercase r double dot is equal to lambda, right? So if I put that now into equation 1, I have lambda plus mg sine theta plus lambda equals 0. Okay, so lambda is equal to minus a half mg sine theta.
And then the door comes open. Let's do this one first. Try rotating it. Yeah.
So we found lambda.
Yeah. Well, we might have to take up the hand out.
So remember, we had our two equations of motion here, equation 1 and 2. Well, now we can put the lambda in terms of things that we know.
Yeah.
So put this back into equations 1 and 2. So I get equation 1 will become, equation 1 is there, right? It's mr double dot plus mg sine theta minus a half mg sine theta, right? So it's mr double dot minus plus a half mg sine theta. And so if I move it to the other side, I will get mr double dot equals minus 1/2 capital M g sine theta. And then the equation 2, which was mr squared phi double dot equals lambda r, if I just replace the lambda by minus a half mg sine theta, I get mr squared phi double dot equals minus a half mg sine theta capital R. And yep, the r's would cancel, capital r's, some of them, but I'm going to leave it in this form. So that's our two equations of motion for r dot, or r double dot, and phi double dot. So let me at least draw your attention to the second equation. What does it look like? So remember, this will all work with what you know how to do from Newton's second law. And so the second equation, what does it look like? Well, we have a hoop. And what's the moment of inertia of a hoop? It's called I, right? So it's mr squared for a hoop. So that second equation, mr squared is I. Sometimes the phi double dot, you call that the angular acceleration, right? And sometimes you call it alpha. And then this last term, maybe it's equal to some torque. And in fact, it is the torque that makes the hoop turn. So this is an obscure way to then end up finding out that there must be some. Remember, where did we start? when we look at our hoop here, we never we never wrote down the forces here. So we never explained really what makes the hoop turn, and if you were using Newton's second law, you would have to explain how the hoop turns. The hoop turns because there's a force of friction at the point of contact that makes the hoop turn. And that's a complicated balance of forces. So we completely ignored that, and we ultimately end up finding out that, yeah, there is a torque on the hoop coming from a force, so that force is a half mg sine theta, right? And there's a torque times r, it's negative, and that gives the angular acceleration times the moment of inertia. So somehow this description is very powerful, and it's uncovered all these relationships that we typically have to come up with for Newton's second law. But remember, we didn't do much, right? We wrote down the kinetic energy of the system, we wrote down the potential energy of the system, and then we knew mathematically that we could keep it in terms of two different coordinates if we added in this Lagrange multiplier thing. But now once we're all done with the equations of motion and we look back and we think of what we did, you can see this Lagrange multiplier that we added in, it does have some physical interpretation. And in fact, that physical interpretation is related to the force that makes the hoop turn. And so we see this relationship now for the first time between a constraint and forces. And so that you can think of a force of constraint that ties r and phi together. This rolling without slipping, there is a force associated with that, and that's of course the force that makes the hoop turn. Remember back a few pages, where did we do this? We wondered if this lambda f term that we're adding in, maybe it really does have, it's like a potential, so maybe there's some sort of force that can come from it. And then we wrote this formula very generally, the Qij, just mathematically, that there's some sort of generalized force that has this form. So at this point we know lambda and we know everything else. So let's go ahead and plug it into this particular equation to see what we get for a force. Just out of curiosity, right? So out of curiosity, let's calculate Qij. And Qij, remember, was defined to be lambda I times d by dt of di fi by di qj dot minus di fi by di qj. So in this case, there's only one I, there's only one lambda, there's only one constraint f, and then j, it could be equal to either r or phi. Alright, so that means we need to find out what Q1R is and Q1 phi is. So there's two of these possible capital Q's. So let's calculate the first one. So the first one, which is Q1R, that's lambda times d by dt of di f by di r dot minus di f by di r. So let me just write f. F was little r minus big R phi. So f doesn't depend on r dots or phi dots. So that first term is 0. So Q1R is going to be lambda. The first term is 0, and then the derivative of di f by di r, that's just equal to 1, right? So Q1R is minus lambda. And so minus lambda is a half mg sine theta, because lambda was minus a half mg sine theta. And then the other force, Q1 phi, right? That's again lambda times d by dt di f by di phi dot, which is going to give us 0 minus di f by di phi. The first term is 0. So that's equal to lambda times 0 minus di f by di phi. So di f by di phi is minus r. No, because it's minus, yeah, it's minus that, so it's going to be a plus r. And so that is equal to minus a half mg sine theta r. So let me just say by inspection, we have I alpha equals Q1 phi. Oops. So Q1 phi, right? This minus mg sine theta, sorry, that's a capital R at the end. The equation of motion in phi double dot was exactly equal to minus a half mg sine theta r, which is what we found, right? So Q1 phi is the torque that makes the hoop turn. So it's really very remarkable now, because it's completely abandoned forces, right? We haven't written down a single force to solve this problem, right? We've only written out kinetic and potential energy. And yet, when we apply the procedure here and we use Lagrange multipliers, we end up finding that these Lagrange multipliers, which incorporate the constraint equation, they're somehow related to a force. And so that's sort of a general theme, that when you have a constraint, there's usually a force associated with that constraint. So think about two masses connected by a rod. The rod is a constraint on the position of the two masses. And the way that constraint works is that there's a force, right? There's a tension in the rod that keeps the two masses next to each other. So these constraints do at least sound like they should be related to forces. And then we see here mathematically that when we apply this whole method of Lagrange multipliers to handle these constraints, we do end up with things that look like forces. And these lambdas may be difficult to interpret, right? In this case, the lambda was very clearly the force that gives the torque that makes the hoop turn. But sometimes the constraints might be complicated, and the lambda might be more difficult to interpret. But the general theme is the same. Any questions about that? So I'm going to stop the lecturing here, because on Thursday we went really long. But the next thing that we're going to do, and so I'd actually encourage you to try and finish that problem, and I'll stay available, but I won't lecture it, and I'll do this problem, example 4.5 on Thursday. The example 4.5 is just redoing the example that we just did. Right? Same thing, hoop rolling down the slope, and we've done it now with 2 degrees of freedom instead of 1, but you can do it with 3 degrees of freedom instead of 1. And so example 4.5 asks you to now do it with x, y, and phi. So instead of using r, we'll use x and y independently in phi. So you'll have to write out a constraint equation that relates to x and the y's, and then one that relates to phi's. So you have two constraint equations, and you'll carry them out, and then you'll find the forces associated with those constraints. And so I'll do it on Thursday, but if you want to use the rest of the lecture to work it out now and ask me questions, you can do that. But I'll stop here. Any questions? And I'll also stop the recording here. All right, so I'll stay online as you try to go through example 4 or 5, and if you have questions, because there are some mathematical steps, and then we'll go over it on Thursday. But I'd like you to take the time to try and do it by yourselves first.